At the end of the last video, I left you with this problem to go and attempt. So let's go through it quickly. If you recall, we had a piston in a cylinder and we had argon gas beneath it, and on the piston was a mass. And it was also said that the walls of the cylinder were well insulated, so that suggests that there's no heat loss through the walls. The only energy input to the argon was this shaft here, which carries an impeller, and the shaft is rotated, and they tell us the speed of rotation 500 revs per minute and the shaft torque. Now remember, from mechanics we can use P equals 2 pi nt over 60 and see what power, what rate of work is going into that shaft and hence being given over to the argon. What's going to happen is that work is going to be done on the argon is going to heat up, it's going to expand, and the piston is going to rise. And because the piston is frictionless, and because the mass of the piston and the mass on top of it doesn't change, the pressure here is going to stay the same, and in other words, the pressure here and here is going to be the same. Now, before we just dive into it, let's just cast our minds back a bit to specific heat. And remember that there were two different specific heat values that we used. And there were times when we used CV, and there were times when we used CP. Remember what CV was? That was the value of specific heat for a process occurring under constant volume. And this was the same, but for a process occurring under constant pressure. Now, let's remember when to use which one. When you wish to use CV, you equate it to change in internal energy. So change in internal energy is equal to CV times change in temperature. And when you use CP, it is now change in enthalpy, being CP delta T. Now, in this question we were given CP, but remember that you can find CV if you have R. What is R? Well, if you go back in your notes a little bit, you'll remember that it was the difference between CP and CV. And in fact, CP was always the bigger. CP was equal to CV plus R. R is the gas constant. You get it from a table. And in our case, we're going to be using argon, and R is 0.2081. So what we're actually saying is, although you were only given CP, you could indeed get CV because you were given R. So we're going to do this problem using CP, and we're going to do the problem using CV to show that either route is possible. Right, to start off with, let's find the pressure in the argon, and remember that pressure is load over area. The load being carried on top of the argon is the weight of the piston, or the mass of the piston and the mass on top of it, multiplied by 9.81 to get to weight, divided by the area of the piston, and we find 1936.02 pascals. That would be gauge pressure. In other words, measured above atmospheric. Absolute pressure, and the reason we need absolute pressure is when we put pressure into our thermodynamics calculations, they must be absolute. Absolute is gauge plus atmospheric. You were told the atmospheric if you look at the question. So you add the two together and you find that the absolute pressure is 101.936 kilopascals. The initial volume is easy to work out because it's a cylinder of length 250 millimeters and diameter 0.2 meters. So the initial volume, that's this volume in here, works out to 7.854 times 10 to the minus 3 cubic meters. The starting temperature was 20 degrees C. We can't work in degrees C, we must work in Kelvin. So we add 273, which puts us at 293 Kelvin. Then, using the equation of state, we can find out what mass of argon we are dealing with. What mass of argon, what matter is in that space over there. So PV is MRT, or M is PV over RT. There's the pressure. Remember where that came from? There it is there. 101.936 times 10 to the 3 times the initial volume, which you've just worked out. There it is. It goes in there. R was given to you at 0.2081 times 10 to the 3. And you multiply by that initial temperature at 293 Kelvin. And you find you're dealing with quite a small mass of argon, 0.01313 kilograms. Now, if this piston is to rise from 250 to 450 millimeters from the bottom, it's clear that there's got to be an increase in volume. Let's see what the second volume has to be. Well, it is the same diameter, 0.2 meters, times the new length of the cylinder that we are dealing with at 0.45. So we have 14.137 times 10 to the minus 3 cubic meters. Now remember that P1 V1 over T1 equals P2 V2 over T2 for this ideal gas as we are dealing with it. But to simplify it further, P1 is the same as P2, and remember the reason for that. This device is effectively a constant pressure device. The pressure cannot change, because if it tries to change, if it tries to increase, the piston and mass would simply rise. So this is a self-regulating system, a constant pressure device. So with that in mind, P1 being the same as P2, they can fall out of the equation. And we're left with V1 over T1 is V2 over T2. T2 is the only unknown here. And it turns out that the second temperature, that is over here, of the argon must be 527.39 Kelvin for this expansion to take place and for that piston to rise by that much. Now let's consider where the energy came into the argon, where it came from. Remember that we had that shaft turning the impeller, so there was mechanical work done on the system, on the argon. We're going to call that work shaft. And P is 2 pi nt over 60, 2 pi times the speed of rotation, 500 revs per minute, the torque at 3 Newton meters, divided by 60 gives us 157.07 watts, which is in fact 157.07 joules per second. So that is the rate of mechanical work entering the argon, 157.07 joules every second. Now, as with any system, mechanical, thermodynamic, whatever, the change in the energy of a system would be what came in minus what went out. Now, in our case, this is a closed system and it's at rest, so there's no potential energy or kinetic energy to worry about because it's standing still. So, as you'll recall from the notes, we can therefore say that energy is actually all internal energy. So instead of using capital E, we're going to use lowercase u, which is our symbol for internal energy. And what it means is change in internal energy is in fact what energy came in minus what energy went out. So that is actually simpler than we're making out. It's a simple matter of the change in energy. The change in internal energy is what came in minus what went out. Okay, in our case, there was no heat input. There was only mechanical work input, and there was also no heat loss. Remember, it was insulated. So, change in internal energy is what came in, and all that came in was the work done by the shaft. But what went out? Well, the walls were insulated, so nothing went out as heat. However, there was work done on a moving boundary. Go back and read the notes on moving boundaries. We've got to account for that, because remember, to move a boundary takes energy, and we've got to account for that. Now remember that change in internal energy is mCv delta T, the mass times specific heat at constant volume times the change in temperature. So mCv delta T is therefore equal to work done by the shaft minus work done on the boundary. So work done on the shaft is therefore equal to mCv delta T plus work done on the boundary, if you rearrange that slightly. Now for the variables, mass we have, CV we have, and here's the change in temperature. Remember, it must go in as Kelvin, 527.39 minus 293. And then the work done on the boundary we've got to talk about. Remember what's happening there. We have constant pressure during this process. We start at a certain volume and we end at a bigger volume. So this shaded area is the work done on the boundary. Okay, now how do we find that shaded area? Well, we take this triangle over here. Note where the red dot's going. That would be P2 times V2, and we subtract from it P1 times V1. In other words, this little rectangle over here. So it's this one minus this one would give you the balance being this shaded portion over here. So inserting the values, we already have those in. Here is pressure 2. Remember, pressure 2 and pressure 1 are the same, so there they go in two places. There's volume 2 and there's volume 1. And if you calculate that, you find that the work done by the shaft has to be 1601.26 joules for this whole event to occur. But now the rate of energy input from that shaft was 157.07 joules every second. Remember, that was the watts. So it would take 10.19 seconds for this whole event to occur. So there's a little summary. The paddle wheel must run for 10.19 seconds, during which time the argon will increase in temperature by 234.39 degrees C. That's if you take those two differences, or the difference between those two values rather, and will increase in volume such that the piston rises 200 millimeters. It went from 250 to 450 height. During this time, the argon remains at constant pressure. We know why that is. Remember, it's a constant pressure device due to the action of the piston. And just in case I didn't make it clear, CP was obtained, correction, CV was obtained by taking CP and subtracting from it R. That is where we got the CV value, because that is what we needed using this approach, was CV. Now, if instead we want to use CP, we're welcome to, but then we've got to bring enthalpy into the equation. Now, going the CP and enthalpy route, everything is identical all the way through here, right up to this point. So I'm not going to go through that. We have been through that in the previous slide. But here is where things change slightly. Let's go and have a look here. Change in internal energy. We got to the point where we said it was the work done by the shaft minus the work done on the moving boundary. So the change in internal energy can also be seen as final internal energy minus initial internal energy, U2 minus U1. Because remember, final minus initial gives you change. So if we rewrite the above, putting U2 minus U1 in place of change in U, we would be back at the same thing. Work done by the shaft minus work done on the boundary. Okay, there's a plan unfolding here. Just watch carefully what's going to happen. U2 minus U1 equals work done by the shaft minus work done to the moving boundary. Remember, that's all the same still. It's from the graph. There it goes over there. Now comes the interesting part. We try and rearrange the equation to achieve U plus PV terms on their own, because remember, those are enthalpy. To refresh your memory, here's the page from the notes. Enthalpy is internal energy plus product of pressure times volume, either in specific terms or in total energy terms. So if we leave work done by shaft where it is, and we move P2 V2 minus P1 V1 to the left hand side effectively, we could get the equation to look like this. Work done by shaft equals U2 minus U1, that was on the left anyway. And then this lot here is going to cross the equal sign, change signs. And we would have work done by shaft equals U2 plus P2V2 minus U1 minus P1V1. So we're almost there. Remember what we're trying to do? We're trying to get a U plus PV term. So this is okay. But on this side, this is negative U minus P1V1, which doesn't help us. We want U1 plus P1V1. So simply put a bracket around it, put a minus sign in front of it. So there is an enthalpy term, and there is an enthalpy term. And because we've got 2's here and 1's over here, it is suggesting change, because this is after minus before, which is change. So if these are both enthalpy terms and we're looking at change, we have change in enthalpy. And the good news is we know that change in enthalpy is mCp delta T, not CV, CP delta T. Now the rest is easy because Cp was given. So there's the mass, we already know that. Cp we know. And there's our delta T. And miraculously we are at the same value of joules, 1601.25 joules at the rate of 157 per second. It's going to take that same 10.19 seconds to achieve the goal.